Yeah, we're ready to go now. We've got everything recording. And again, the video I'll post it all within 15 minutes after class is over. Okay, so as usual, I want to start off with any questions on any of those chapter 1 lessons or anything about, something you've come across that you need explanation on. Questions, anybody? So I'm not hearing any, so I'm going to get started then. The topic today is lesson 1.5, inverse functions. And once again, you want to look at the core exercises. There's a fair number of them for this particular lesson. So the idea with inverse functions, it's actually really important. An inverse, normally what you do is you pick a value for x and you calculate y. With an inverse function, you can actually reverse that, solve for x, and then you could pick a value for y and solve backwards for x. That's kind of the idea. And in calculus, we need to be able to look at the inverse functions. So that's the reason that this is in here. So the first thing we'll take a look at is finding an inverse. And I think I'm going to expand this, and then the only bad news is we'll have to do a little bit of scrolling here. But anyway, here we go. So finding the inverse of a function, I like the way this puts it. The inverse of a function literally undoes. It literally undoes the action of the function. So if f of 2 is 3, then f inverse of 3 is 2. So the ordered pair is literally reversed from 2, 3 to 3, 2. Every function has an inverse, but not every inverse will be a function. So you remember what a function is. A function passes the vertical line test. That is, for each x, there can be only one y. Well, you take something like a parabola, and it's beautiful. It's a function, and everything works just wonderfully. See, they're having difficulty. Sorry about that. So anyway, you take something like a parabola, opening upward, which is a function, but when you find its inverse, it's not a function. It's still important. It's just not a function. Okay, so and then it goes on to say the inverse may. Here it says the inverse might fail the vertical line test. Like a parabola, when you find its inverse, turns out to be a sideways opening parabola, and it fails the vertical line test. This is called a function being called one-to-one. We'll talk about that more later. So anyway, let's get into it now. I've got an example here of a function, f of x equals 2x plus 4, good old straight line. How do we find its inverse? Step 1. In place of f of x, it works a little better. Plug the old-fashioned y in there. And then you literally interchange or swap the x and the y. So where there was a y, put an x. Where there was an x, put a y. And then just do your best, algebra, to try to get it so that you can solve for the new y. So if you see, I'm doing that in this problem. After swapping, I needed to get the y alone, so I subtracted 4 on both sides. And then finally, I needed to get rid of the 2 right here on the y. And so I divided both sides by 2. So here we go. I mean, there, I've done it. And now the technical notation for that is f inverse of x equals 1/2 x minus 2. So when you see this notation, which looks like it is a -1 exponent. Be careful, because technically, what does a -1 exponent do? It provides a reciprocal. But a reciprocal is only one kind of inverse. So there's a little bit of a failure with this notation. It doesn't mean reciprocal, it means inverse. And the trouble with reciprocal is that's only one kind of inverse, but here it's more general. So one time, you replace f of x with y, swap the x and the y, go about solving for the new y, you've got your inverse. All right. So I guess here I actually did it one more time, you know, put the y in place of x, swap them. Oh yeah, this is a little different one. Swap the x and the y. And then you got a new y on the right, 2y plus 4. So you want to get that 4 out of there. Subtract 4, divide by 2. Okay, so now you got your f inverse. All right. Now, here's that function we just did on the left, 2x plus 4, and here over here on the right, there's our inverse. Okay? Now, one characteristic of inverses is that when you compose the original function with its inverse, you will get an answer of x. Now, I think we've talked about composition of functions. Normally, you can't expect, when you reverse the order, f of f inverse is not normally equal to f inverse of f. But it is when the functions are inverses of each other. I'm sorry, I should have said that. F of g of x is not the same as g of f of x unless they're inverses of each other. So when we simplify this, carry out the distributive property here on the right, you'll see that it really does come up to be an x. Okay, that basically proves that we found the inverse correctly. So if you get to a problem in your assignment where it says, show me that this function is an inverse of the other, this is an awesome way to do it. Just take the two functions, compose them. Anastasia, I'm sorry you're having trouble. Thanks for trying to hang in there. She has exited and entered. It looks like she's having technical difficulties. So anyway, so this is a great way to prove two things are, one thing is an inverse of the other. Compose them. By the way, you can do it the other way too. You can also compose it the opposite way. You can do f inverse of f. It's a different substitution, but it still comes out to this. So you can, in order to prove a function is an inverse of the other, you can do it either way. F inverse of f or f of f inverse. I don't know. Do you all see that I substitute? So let me just explain here. On the top, when I did f of f inverse, that means I was using the outside, the f function. So I was using 2x plus 4. And what did I substitute in for x? The f inverse. See, the f inverse is literally in the inside here. So that's what you substitute in. So you see how I did that right here? I substituted in that 1/2 x minus 2. Whereas on the bottom, on the one below the line, when I did it the opposite way, this time the inverse was on the outside. So I was using this function over here to start with. And I plugged in the original function. So you see how I plugged in 2x plus 4. And okay, so anyway, sometimes that's a little confusing. They really are different, but they both will come out to x. And let me repeat, when you do two things and compose them, they will not come out to the same answer when you reverse it. The only time that'll happen is when the two functions are inverses. So this is an awesome way to prove that you really have an inverse. Okay. So now let's move on to a function that's a little more challenging. This time we are going to look at a quadratic. This one up here on the top. X squared minus 3x plus 9/4. So once again, put the y in place of the g of x. Then, well, I rewrote this. Okay, So I did do a little algebra here. You see how, I don't know how many of you are into this, but this right here, people from my last semester will know, I would call that a ding, ding, dinger. And the reason is that you should be able to spot that that's a perfect square trinomial. Why? Because the first term, x squared, and the last term, 9/4, are perfect squares. And secondly, when you take their square roots, namely x and 3/2, and multiply them and double them, you get -3, the middle term. So bing, this really works. Therefore, you can rewrite this problem this way. Now it's quite a bit easier to work with algebraically. Now reverse the x and the y. Swap them. And then got to solve for y. So step 1, take square roots of both sides. Don't forget, you have to take both square roots there. And then add 3/2 to both sides. Bingo. We've got our inverse. All right. So now I want to show you what happens when you graph a function and its inverse. So remember the first one we did? We started with 2x plus 4. And in the graph at the right, you should be able to see that that's what? The red, I have a dull red line right here, this one. And you see how it goes through the y-intercept of 4, and it has a slope of 2. So for every, up 4, it's to the right 2. Yep, slope of 2. So that's that line. And here was the inverse, and the inverse is in yellow. The green line is what? Good old y equals x, in other words, otherwise known as the identity function. Do you see why I drew it in? Because the identity function becomes what? The mirror line. The original function and its inverse are always mirror images with respect to the identity function. So, that's not a way to really find it, but boy, it's another way to check. Did I really find the inverse? Well, if you plot them on the same set of axes, and they will do that in the assignment today. If you plot them on the same set of axes, you should get this mirror image effect. Let's look at the other one. The other one we did was this quadratic, and that's this one right here, the red one, and it's of course a parabola, and the inverse, I had to plot with 2 colors because it's plus and minus the square root of x plus 3/2. So here's the plus part up here, and here's the minus part. And when you put them together, what do you have? You have a parabola that's literally what? Tilted 90 degrees to the right. And sure enough, look what happens when you put the identity function on there. If you tilt your head a little bit to a 45-degree angle to the right, you can see we have perfect mirror imaging. So inverses will always do that. Hopefully that makes sense to you. All right. So a cool thing about inverses is, as I mentioned earlier, you literally have a reversal of ordered pairs. So if a function has f of 2 equals 3, and if you did the inverse right, then f inverse of 3 equals 2. So you see what's going on here. With the original, you had an ordered pair of 2, 3. And with the inverse, you have an ordered pair of 3, 2. It just literally reverses the ordered pair. Or if you had a function g of 7 is 100, that basically is this ordered pair. If you find the inverse properly, then g inverse of 100 is 7. And again, you have a reversal of ordered pairs. So the inverse really is a good name for this. It just literally inverts the process. So what I want to do now is let's do some examples. a few from the assignment, okay, and we'll see. Well, first of all, are there any questions? Yeah, I guess let's look at this problem right up here. Y equals mx plus b, a good old straight line. So if we take the original function, y, let's take this one, it has a slope of -1 and a y-intercept of 6. If we, yeah, I'm not sure this example is the best. But what I did is I drew, yeah, let's just go on. This is not the best example, so. I do want to talk about this now, one-to-one functions. So if we take the standard famous function y equals x squared should look what? I'm just making a couple points here. So I didn't quite hit all the points, but there's the famous function f of x equals x squared. Is it a function? Yes. Does it pass the vertical line test? Yes. So what's its inverse? By now you probably figured this out. It's going to take the function and flip it 90 degrees to the right. So what you're going to wind up with, if we draw the inverse on here, let's see, it's going to look like this. And then if you put the identity function on here, it gives you this mirror imaging effect. Now, you tell me, the red function is the inverse. Is that a function? I mean, the blue one is, but the red one is no longer a function. It fails the vertical line test. All right. So when a function's inverse is not a function, as we see right here, then the function that we started with, this one right here, is not a one-to-one function. So in effect, a one-to-one function can actually be figured out from the original function to see, take the blue function here. Does it pass? If there was a horizontal line test, would it pass? No. Why? So why does that work? Because since every function to find its inverse is rotated 80 degrees to the right, and then that function, you want to see if it passes the vertical line test. Well, that's the same as checking if the original one passed the horizontal line test. So a really quick check. If I give you a function and ask you, is this a one-to-one function? You can tell by kind of giving it the horizontal line test. Okay, so let's do another one real quickly here. This time, remember yesterday we were talking about the sine function, and sine is 0 is 0, and then 90 degrees, we're up to 1, and then back, and we have this kind of a situation going on. So the sine function has this kind of an appearance to it. Now, I guess I didn't dip this low enough. My apologies here. Let's do that correctly. There we go. Now that looks a little bit better. So, is that a function? Sure. What would happen if we tipped it 90 degrees to the right? Can you see that it's going to fail the vertical line? In other words, does the sine curve pass the horizontal line test? No. So the sine is a function, but it is not a one-to-one function. So you're going to see they're going to be asking you in the assignment when you go through this, is this a one-to-one function? All you got to do is basically, usually if it's a graph, all you got to do is look at it from this horizontal line test viewpoint. Okay, so let's do an example now. One of the problems you're supposed to do is number 31, so I'm going to take that one next. Number 31. And number 31 has this. Let's see, I got to make sure I get the wording right. Find the inverse function of that. So, well, they also, so the first thing we do is change it to y equals the square root of x. Okay, then you do the swap. And then you're probably what? Going to, we need to solve for y, so we could square both sides. Okay, now, and then they ask you some other questions. They say, graph the function and its inverse on the same set of axes. Okay, so I'm going to pull up Desmos to do that. So we've got the square root of x. And that's the way it was. Well, when, by the way, when there's no plus or minus in front of it, that means only the principal square root. So that's why we only get half of a parabola here. And for the inverse, remember we got x squared. Okay, let's throw the identity function on there. You notice we have a little problem, and that's what they hint at in the question. The question says, describe the relationship between the graphs. Well, I mean, it's looking good. It's got a mirror imaging on it, but it doesn't have everything on it. So what happens here when we found the inverse? We only found what? Kind of a half. All right. And so what's different? Look at the blue curve. What is the domain of the blue? That's the x squared curve. The domain is what? All real numbers? Because that parabola forever gets wider, and it would include all negatives, all positives. So that's good. What's the domain of the red curve? Well, only from 0 on, right? And that makes sense because you can't take the square root of a negative. Okay, go back to the blue curve. What's the range? The range would be what? From 0 through infinity, right? It never gets lower than the origin, and it goes up forever. What's the range of the red curve? From 0 to infinity, because that's half of a parabola getting wider. Okay, so please note, sometimes when you find an inverse, you won't get the whole mirror image. And you need to be very conscious of that. Okay, you need to, and that's what they're trying to point out to you when you work on number 31. Anybody want to throw some questions in here? Okay, I want to do another problem with you from the assignment. I mean, we could do more about it. I want to just, I'm just going to do this next example. And for this one, I would like to do number 65. And number 65 says we have f of x, and it's equal to x cubed plus 2x minus 1. And they tell you that a is 2. Okay, now if you look in the directions, it says in 65 to 70, find F inverse of A. So in this case, what's F inverse of 2? So now I'm going to tell you, this is a real stinker to find the inverse of. Because if you were to go through F of X, try, you try doing the, well, here, let's just do it. I'll just show you what I mean. If you take y equals x cubed plus 2x minus 1, swap the variables, you would have this. Now, here's where the fun starts. Can you solve that for y? It's a stinker, because you could add 1 to both sides, and then you could factor a y out of the right, but that really doesn't lead you to a point where you can solve for y. And so you're kind of stuck here. Okay? But what you can do, you don't even need to do that, because here's what it's saying is, hey, what this says is, if the answer is 2, can you tell me what x is? So, F inverse of 2 means, hey, when 2 is the answer, can you tell me what x is? And you can just figure that out in your head. What number for x would make this work? Can you see that's x equals 1? So F inverse of -2 is 1. Why? Because 1 cubed is 1. 1 plus 2 is 3. 3 minus 1 is 2. Oh, so 2. So when you plug in 1, you get 2. So what's the inverse of 2 then? 1. So this one, even without being able to calculate the official inverse of the function, you can still kind of do some reverse calculation to get that to work. Okay, so I think that's where I'm gonna. I would like to see if you have any questions now. So it's kind of a little bit of a quick lesson today, but I know you guys have had inverses before. Work your way through the. If you go back and look at the core exercises for lesson 1.5, there's plenty to work on, but basically I think we've hit the basics here. I can just quickly show you here. Yeah, so let me do a little erasing. What we want to look at right now is for today is these guys right here. So there's your emphasis for getting ready for tomorrow. Questions? All right. Well, then I thank you. Anastasia, thank you for trying to get in about 9 times. Obviously, she had technical difficulties. It was good to have the rest of you in here. I wish you'd speak up a little bit more, but this is still pretty much review, so I get it. Thank you. I'm going to end the broadcast then. Have a good one.